Chapter 14, Section 3, Electrical Power, AC and DC Electricity. Vocabulary will be kilowatt, kilowatt hour, direct current, alternating current, and transformer. Our objectives are to calculate power in a circuit, calculate the cost of running an appliance, and distinguish between alternating and direct current. If you look at a stereo, hairdryer, or other household appliance, you may find a label giving its power in watts. In this section, you will learn what the power ratings on appliances mean and how to figure out the electricity costs of using various appliances. Electric power. A watt is a unit of power. Electrical power is measured in watts, just like mechanical power that you didn't actually learn about in Chapter 4. Electrical power is the rate at which electrical energy is changed into other forms of energy, such as heat, sound, or light. Anything that uses electricity is actually converting electrical energy into some other type of energy. The watt is an abbreviation for 1 joule per second. A 100-watt light bulb uses 100 joules of energy every second. So you can think of power as how fast energy is being transferred or transformed. This is shown in figure 14.10. The three electrical quantities. We have now learned three important electrical quantities. Current. Current is what carries power in a circuit. Current is measured in amps. Voltage. Voltage measures the difference in energy carried by charges at 2 points in a circuit. A difference in voltage causes current to flow. Voltage is measured in volts, and 1 volt is 1 watt per amp of current. Resistance. Resistance measures the ability to resist current. Resistance is measured in ohms. 1 amp of current flows if the voltage of 1 volt is applied across a resistance of 1 ohm. Paying for electricity. Electric bills sent out by utility companies don't charge by the volt, the amp, or the ohm. Electrical appliances in your home usually include another unit, the watt. Most appliances have a label that lists the number of watts or kilowatts. You may have purchased 60-watt light bulbs or a 1,000-watt hair dryer or a 1,200-watt toaster oven. Electric companies charge for the energy that you use, which depends on how many watts each appliance consumes and the amount of time each is used during the month. What you're really paying for is how much energy you use. It means that if you're using 60 watts, that's 60 joules per second, and if you have it on for an hour, then you have used 60 joules per second for an hour, and you're paying for how much energy has been used during that hour. Calculating power in a circuit. Calculating power. Since 1 volt is a watt per amp, to calculate power in an electric circuit, you multiply the voltage by the current. To calculate the power of a device in a circuit, multiply the voltage drop across the device by the current through that device. So our equation is P is equal to IV. Watts and kilowatts. Most electrical appliances have a label that lists the power in watts, as shown in figure 1411, or as you saw in your homework a few weeks ago, or kilowatts. The kilowatt is used for large amounts of power. 1 kilowatt, or kW, equals 1,000 watts. Another common unit of power, especially on electric motors, is the horsepower. 1 horsepower is 746 watts. The range in power for common electric motors is from 1/25 of a horsepower, or 30 watts, for a small electric fan to 1 horsepower, 746 watts, for a garbage disposal. Buying electricity. Kilowatt hours. Utility companies charge customers for the number of kilowatt hours, abbreviated kWh, used each month. 1 kilowatt hour means that a kilowatt of power has been used for 1 hour. A kilowatt hour is not a unit of power, but a unit of energy. A kilowatt hour is a relatively large amount of energy, equal to 3.6 million joules. If you leave a 1,000-watt hair dryer on for 1 hour, you have used 1 kilowatt hour of energy. You could also use 1 kilowatt hour by using a 100-watt light bulb for 10 hours. The number of kilowatt hours used equals the number of kilowatts multiplied by the number of hours the appliance was turned on. You pay for kilowatt hours. Electric companies charge for kilowatt hours used during a period of time, often a month. Your home is connected to a meter that counts up total number of kilowatt hours used, and a person comes to read the meter once a month. If you know the cost per kilowatt hour the utility company charges, you can estimate the cost of operating any electrical appliance. Alternating AC and direct DC current. Direct current. The current from a battery is always the same direction, from the positive to the negative end of the battery. This type of current is called direct current, or DC. Although the letters DC stand for direct current, the abbreviation DC is used to describe both current and voltage. A DC voltage is one that stays the same sign over time. The terminal that is positive stays positive, and the terminal that is negative stays negative. Your experiments in the lab use DC since they use batteries. Alternating current. The electrical system in your house uses alternating current, or AC. Alternating current constantly switches direction. You can theoretically create alternating current with a battery if you keep reversing the way it is connected in a circuit, as shown in figure 14.13. In the electrical system used in the United States, the current reverses direction 60 times per second. It would be hard to flip a battery this fast, and this is why we say we have a 60 Hertz electric system. A DC current or voltage keeps the same sign over time. An AC current or voltage reverses sign, usually 60 times per second in the US. Electricity in other countries. For large amounts of electricity, we use alternating current because it is easier to generate and to transmit over long distances. All the power lines you see overhead carry alternating current. Other countries also use alternating current. However, in many countries, the current reverses itself 50 times per second rather than 60s, and wall sockets are at a different voltage. When visiting Asia, Africa, or Europe, you need special adapters to use electrical appliances you bring with you from the United States. Peak and average voltages. The 120-volt AC electricity used at homes and businesses alternates between peak values of 170 volts and negative 170 volts, as shown in figure 14.4. This kind of electricity is called 120 VAC because plus 120 volts is the average positive voltage and minus 120 volts is the average negative voltage. AC electricity is usually described by the average voltage, not the peak voltage. Electricity, power, and heat, although we're going to talk about it as thermal energy rather than as heat. How do you get more power? How do you get more power when you need it? From the power formula, we can see that increasing voltage or current will increase power. The problem with raising voltage is that the electricity in a standard wall outlet is 120 volts and it is hard to change. While certain appliances use 240 volts, the higher voltage is more dangerous, so 120 volts is used for most electrical appliances. Higher power usually means more current. The most common way to get higher power is to use more current. However, thermal energy becomes a problem when wires carry large currents. A wire's voltage drop from Ohm's law equals the current multiplied by the wire's resistance. Because a wire's resistance is small, the voltage drop is usually small enough to be ignored. But if there is a large current, there can be a significant voltage drop. Remember, power is voltage drop multiplied by current. In a wire, this power is converted into thermal energy. A small amount of thermal energy can safely be transferred away from the wire by conduction or convection. Too much heat, too much thermal energy, could melt the wire or start a fire. Reducing thermal energy in electrical wires. Wires are made in different sizes to carry different amounts of current. A large diameter wire has less resistance and can safely carry more current than a smaller, thinner wire. This is why fuses have really small, thin wires, so that they break if too much current goes through them. Same thing with your light bulbs. Your incandescent light bulbs have a really thin wire as their filament, and when that tiny wire breaks is when we say a bulb has burned out. A 12-gauge wire is thicker than a 14-gauge wire and can carry more current, as shown in figure 14.15. You should always use the right wire for the current that is flowing. This includes extension cords, which you may use without thinking about whether they are safe or not. Extension cords are made with 18-gauge wire, 16-gauge, 14-gauge, and 12-gauge wire. So the gauge is fraction of an inch. So a 12-gauge wire is 1/12 of an inch, a 16-gauge wire is 1/16 of an inch, and that's why a 16-gauge wire is smaller than a 12-gauge wire. Length and resistance. The length of a wire also affects its resistance. The longer a wire is, the more resistance it has. Think about moving around your school and how you can get through a short, crowded hallway quickly, but it takes a long time to get down a long, crowded hallway. Check your extension cords for safety. All extension cords are rated for how many amps of current they can carry safely. Always check to see if the extension cord can carry at least as much current as the device you are using requires. For powerful tools such as a saw, you should use a 14-gauge or 12-gauge heavy-duty extension cord that is rated to carry 15 to 20 amps. Many fires have been caused by using the wrong extension cord. Electricity in homes and buildings. Circuit breaker panel. The 120 VAC electricity comes into a normal home or building through a circuit breaker panel. The circuit breakers protect against wires overheating and causing fires. Each circuit breaker protects one parallel circuit, which may connect many wall outlets, light switches, or other appliances. Hot, neutral, and ground wires. Each wall socket has 3 wires feeding it. The hot wire carries 120 volts AC. The neutral wire stays at 0 volts. When you plug something in, current flows in and out of the hot wire through your appliance, doing work, and back through the neutral wire. The ground wire is for safety and is connected to the ground at 0 volts near your house. If there is a short circuit in your appliance, the current flows through the ground wire rather than through you. Ground fault interrupt, or GFI outlets. Electrical outlets in bathrooms, kitchen, or outdoors are now required to have ground fault interrupt, or GFI outlets installed, as shown in figure 14.16. A GFI outlet contains a circuit that compares the current flowing out on the hot wire and back on the neutral wire. If everything is working properly, the two currents should be exactly the same. If they are different, some current must be flowing to ground through another path, such as through your hand. The ground fault interrupter detects any difference in current and immediately breaks the circuit. GFI outlets are excellent protection against electric shocks, especially in wet locations. Distributing electricity. Why electricity is valuable. Electricity is a valuable form of energy because electrical power can be moved easily over large distances. You would not want a large power plant in your backyard. One large power plant converts millions of watts of chemical or nuclear energy into electricity. The transmission lines carry the electricity to homes and businesses, often hundreds of miles away. Power transmission lines. Overhead power lines use a much higher voltage than 120 volts. That is because the losses due to the resistance of wires depend on the current. At 100,000 volts, each amp of current carries 100,000 watts of power compared to the 120 watts per amp of household electricity. Big electrical transmission lines operate at very high voltages for this reason, as shown in figure 14.7. The wires are supported on high towers because voltages this high are very dangerous. Air can become a conductor over distances of a meter at high voltages. Never go near a power line that has fallen on the ground in a storm or other accident. The basic idea here is that for the same amount of power, you can either have a very high current with a low voltage, or a very low current with a high voltage. Because a low current means low losses, we prefer to have a low current with a high voltage to carry the same amount of power. Transformers. A device called a transformer converts high voltage electricity to lower voltage electricity. Within a few kilometers of your home or school, the voltage is lowered to 13,800 volts or less. Right near your home or school, the voltage is lowered again to the 120 or 240 volts that actually come into the circuits connecting to your wall outlets or appliances. Changing AC to DC. Many electronic devices like cell phones or laptop computers use DC electricity inside, but also can be plugged into the AC electricity from a wall outlet with an AC adapter, as shown in figure 14.18. An AC adapter is a device that changes the AC voltage from the wall outlet into a DC voltage for the device. The adapter also steps the voltage down from 120 volts to the battery voltage, which is usually between 6 and 20 volts. Connections. How do hybrid cars work? Gas-electric hybrid cars look and drive like any other car, but use 20 to 30% less gas than their non-hybrid counterparts. For example, a hybrid car's gas mileage is about 50 miles per gallon. The gas mileage for standard cars ranges from 10 to 30 miles per gallon. To understand how hybrid cars get better gas mileage, we have to look at the engines. Cars powered by gasoline. The efficiency of a gasoline engine is only about 13%. That means when the car is in motion, it only uses about 13% of the available energy from a tank of gas. The rest of the available energy from a tank of gas is lost as thermal energy. The more energy that is lost as thermal energy, the less efficient the engine or any system is. Although the combustion of a gasoline engine produces many pollutants, gasoline is very energy-rich and easy for a car to carry. These two features have made the gasoline engine so easily adopted when oil was inexpensive and there was less concern for the impact of cars on the global environment. Cars powered by electricity. Compared to gasoline-powered cars, electric motors are very efficient, 80% from batteries, and they produce no pollutants. To run an electric car, the batteries need to be charged. Often this is done by plugging in the car during the night. Unfortunately, batteries are heavy and don't have as much energy as gasoline. For instance, the available energy in a typical car battery is equivalent to about a small cupful of gasoline. Until there is a better electrical storage system, cars powered by electricity from a battery must be small and only used to travel short distances. The best of both technologies. A hybrid car uses the best of both worlds, a gasoline-powered engine and an electric motor. By combining technologies, the efficiency is improved to about 26%. The electric motor helps the gas-powered system be more efficient by using electricity to transfer energy within the system. How do hybrids compare? In a hybrid car, the gasoline engine and electric motor work together to accelerate the car. This allows the gasoline engine to be smaller and more efficient. Every time a standard car slows down, kinetic energy is lost as the brakes heat up. In contrast, the hybrid's electric motor operates as a generator during braking. When the car slows down, kinetic energy is converted to electrical energy that charges the batteries. Then, to speed up the car, the stored energy in the batteries is converted into useful kinetic energy by the motor. In addition to getting great gas mileage, hybrid cars are rated as ultra-low emission vehicles. This means that they do not produce as many pollutants as standard cars. Hybrid cars produce less pollution because the engine is smaller and simply uses less gasoline. Also, when a hybrid car comes to a stop, the engine automatically shuts off to save gas. When it is time to go again, the car turns on instantly. At very low speeds, as when you are driving in a city, the electric motor runs the car instead of the gasoline engine. When the electric motor is used, there is less pollution. Hybrid technology is just a beginning. The gas-electric hybrid is only one of the many types of more efficient motor-powered vehicles that are being developed today. Driving this development is an interest in decreasing our use of fossil fuels for transportation. Interest in developing alternative transportation technologies will continue because they are potentially more efficient and less polluting. In the meantime, since we all need to travel and often use gasoline-powered vehicles, how can you reduce your use of fossil fuels so that you save money and reduce pollution? Here are some options. Share rides, take public transportation, and drive a medium-sized or small car that has gas mileage. Here are some questions to think about. These are not homework, I just want you to think about them. If you only need to drive 2 miles per day, which kind of car would be the best to use? Why is the efficiency of gasoline-powered cars so low? Hybrid cars are better for driving in cities, but not as efficient for highway driving. Why? Some hybrid cars have efficiency meters, a gauge that show you your miles per gallon so that you can monitor and improve your driving habits. Make a list of driving habits that help you save gas.